Welcome to the main event. Finally, we get to measure the effect size, which is what we're trying to do since the beginning. Remember, we have the group of employees who have undergone statistical training and the control group who did no statistical training. So let's assume the mean employee lifetime value for each group is mu s and mu ns. What we're interested in knowing is what is the difference between these means. So we're going to use the capital letter delta, the capital Greek letter delta. So these are the unknowns, the two populations, and we want an estimate of that. What we have though is an estimate computed from the sample. So the 31 employees in the sample from the NS group and 30 employees from the statistic group. We computed the mean within each of these groups. When we subtract the means, we obtain 130. So D is an estimate for delta. Okay, and effect size is in general, could be, depending on this test, it's a different quantity. In this case, this is what we call the effect size. What is the difference between the two groups? This is the most important thing we care about. Up until now, the hypothesis testing was just convincing skeptical colleagues, right? It was just allowing us to proceed here. There is a difference of some sort. Now we want to measure how big is that difference. And this is the quantity we care about, right? If we're going to invest money in this statistical training or time we require the employees, there better be a benefit. Imagine we calculate the effect size and it's like 2 units, so you invest thousands of dollars, millions of dollars to provide this training, and the effect is very small. So this is why we need an estimate, so we can know, is it worth it? There is a difference between the two groups, we already established that, but how big is that difference? Okay, so that's question 2. So the estimate 130 is a good first step. This is called a point estimate, in other words, a single number. But the better answer to question 2 is not a number, but an interval. We want to tell you, the answer needs to be a range. We say, well, we think it's 130, but it could be anywhere between here and here. So that's called a confidence interval. And usually it comes with a guarantee, like 90% if we follow the statistical analysis on other data sets using this procedure, our procedure for producing this interval will be 90% accurate. So that's how we're going to choose the parameters. We're going to go for a 90% confidence interval. And we're going to do it 2 times. Why? Because we want to, it's easier to understand things when you see them done twice. Okay. The Bootstrap method is an easy way to describe the variability within a sample. So whenever we want a sampling distribution, like the sample mean, the definition is to obtain multiple samples from the population. Like that's what the sampling distribution is by definition, is if you were able to collect repeated sample and sample and sample and sample. And within each sample, compute the value of the statistic. In our case, we're going to be interested always in the mean of the sample. So if you do that repeatedly, you will require like collecting a lot of samples. Instead, so it's very expensive. Like we would need to hire more employees and only then be able to do estimates. The Bootstrap, this is the analogy is pulling yourself up by your bootstrap. So if you don't have a population, but you do have a sample, what if you treat the sample as a population? So in other words, you sample from the sample, hence the name resampling. And you allow replacement So if you sample without replacement, then your sample and your resample will contain the exact same values. But what you treating it like a population, you can do select n values from a sample of size n, but they don't need to be different. So you can pick up the same value twice. So by doing that a large number of times, we're going to do this 5,000 times, you actually get the variability of the statistic function, so the sample mean. And if you, this is the function that performs that bootstrap estimate. So given any sample, this is, think of it, a list of values, and any statistic, I will give you the sampling distribution for it. So we're going to do that. In order to obtain a confidence interval, this is what we're going to do. We're going to we build a bootstrap distribution for the two group means, and then we're going to subtract them to obtain the difference of means distribution. So without generating any new samples of data, just by resampling within the samples we already had. So like sort of we obtain a distribution that describes the variability of the data. So at 130, remember this is our estimate. The point estimate was here. But what can we guess? What if we were to take another sample? Maybe we'll get 140, maybe we'll get 110. Like this variability. How do we describe it? How do we model it? Well, there's a very easy way with the Bootstrap. You just try different subsets of the sample, and some of them repeated. So this is what we obtained here. And by computing the difference between them, we get an estimate of the variability of the difference between group means. So that's what you're seeing here. Now, we know that the actual difference between the populations means, although it's peaked at 130, it could have a quite variability. It can vary from, could even be negative, as far as this bootstrap estimation is concerned. Now, when our goal is to give a 90% confidence interval. So what we're going to do is take 90% of the weight. So we're going to go at 100, cut off somewhere here and here. The function percentile does exactly this. So 90% means we need to cut off 5% from the bottom and 5% from the top. The answer we get is a range 27 to 235. So this gives us a range based on this distribution of things that are likely or the real value of the difference. Okay, so this is what we can tell, we can put in the report. Amy can put in the report and say, we think the difference is 130, but really it could be anywhere between these two values. Okay, here is another way to compute the Bootstrap using the function. Instead of building from scratch, you can just call the Bootstrap function in SymPy, and it will tell you roughly the same, right? The numbers are never going to be exactly the same because it's using randomness, but just to show you don't need to do everything from scratch. I just wanted to explain it. So this is it. The Bootstrap gives us a natural way to characterize the variability of the difference of means. So more to talk about that, but here is another way to do this. Go in a textbook and find the formula. So we earlier we had a model based on the t-distribution for the variability of the sampling distribution capital D. And based on that model and the t-distribution, so this is using the t-distribution in the opposite direction. It's like where, if I wanted a 90% confidence interval, you're using the inverse of the t-distribution to get a number, a cutoff value t star, and you say go in your estimate minus t star standard deviations plus t standard deviation. So using that formula, we can obtain a range of for a particular value. So we want 90%, we get a 90% confidence interval. There's so many assumptions and code that goes into this that it's hard to explain, but the model is the same as what we used for hypothesis testing. The difference is now you no longer assume that they're the same mean, right? I mean, the no hypothesis was a special case where we say the two groups have the same mean. Now we relax that assumption, but the analysis of the different variances, the pooled variance or unpooled variance, everything stays the same. So when you do that, if you remember the looking under the hood, this is very similar calculation. Alpha is the opposite, the complement of the 90%. To get the t star, we use the t distribution. All this to say is by following this formula here that I took from a textbook, you end up with another confidence interval 22 to 237. If you compare, it's kind of similar, off by a few points. Without going into these details, there's another procedure which uses the unpooled variance, but the degrees of freedom are more complicated. So I won't talk about it here, but there's a equivalent way, the same way there were two ways to do the analytical approximation for hypothesis testing above. There are two ways to do confidence interval. Okay, so in the end, we got our point estimate d equal to 130, and we've got four different ways to compute the confidence interval around that. The bootstrap that we did ourselves, the bootstrap from SymPy, t distribution with the pooled variance, t distribution with unpooled variance. As you see, all of them, all these different ways, kind of like it doesn't matter which one you use. You're always going to get roughly the same numbers. You have to say in your write-up, I use this method. But roughly plus or minus 2 here and plus or minus 5 here, the boundaries of the intervals end up being very similar. Okay? I'm going to skip this part because the numbers we've been using so far have been good enough, but there's a way to describe the difference 130 in a standardized way. So optional, you can read this, unfold and read the details. Okay, conclusion finally. Why did we do all of this? It's because Amy had 2 statistics questions, and now she has the answers to them. Is there a difference between the 2 groups? Yes, there is a statistically significant difference between group S and group NS, and the p-value, so the statistical significance is at the level of p 0.048. So that's the answer as you would see in a statistics paper, in a science paper using statistics. Then how much does the statistic training improve EOV? So in other words, what's the effect size? And the answer, as we just saw, is 130, which that's the Cohen's d is the standardized effect size. And this is the new part, why we did all this confidence interval stuff. The confidence interval, 90% confidence interval, I picked, when I wrote this, there was different numbers here, is between 25 and 234. So that's the precise answer. So you give the number 130, but also say between 27 and 235. So you don't know what the true value is. The honest estimate. This is statistics, being honest about what you know. If you say just 130, it's not honest, because it's as if you know the exact value of the population difference between population means. You don't. The only thing we know is a range, because there was a lot of variability in the data. So the real effect of offering statistics training could be anywhere between 25 and 234. Not as good as 130, but you have to be honest. You cannot claim, yes, you exceed 130 difference. You have to say, well, I think most 90% confidence interval is between these two values. Okay, so you can read the rest on your own, but the whole point of providing answers in this way, I'll tell you, is that people, it's the standard way to convince people. Essentially, without statistics, it could be my opinion or Amy's opinion. She will go to a colleague, or the colleague will be like, wow, is this true? And why do you believe? So here is the scenario. The skeptical colleague says, I don't think this is true. Maybe what you observed is due to chance. And then Amy can say, well, no, if there is no difference, if the null hypothesis is true, then it's very unlikely under the null hypothesis what we observe. Therefore, there is a difference. And then the employer could be like, well, how big is this EOV? I don't know if it's really. And she can say, well, 130, but really here is the interval that I can guarantee. It's somewhere in that interval with 90% of the guarantee. So it's to be precise, the guarantee I gave is the procedure I used to obtain this guarantee is accurate 90%. So it's not, I don't guarantee that the answer is in here with 90% probability. I'm saying the accuracy of the procedure I used to build this interval is 90%. Little details to be discussed more. Okay. Everything in this notebook is double the work, right? We showed 2 approaches for hypothesis statement, 2 approaches for estimation. The reason is this is for educational purposes. I want you to know the classical analytical approximation method. If you're taking a stats class, this is what you'll learn. But the permutation test and the bootstrap are the modern statistics. So if you're really lucky and you take a stats class with a young professor, they might show you this. Because the old stuff, the analytical approximation, there's too much formulas and there's no intuition. So people finish a stats class and they don't know, they're just like, oh, I used the t-test, and they don't know what's going on under the hood. So the permutation and the bootstrap, they're techniques that are very hands-on, and you know what's going to happen in the end. So the important thing for you to remember is that everything you saw in these notebooks, that's it. Like that they're not going to be more complicated code. So people in the survey, when I circulated the survey, I said there will be some programming, not more than this. Like what you saw in this notebook, this is how complicated it will get in the book. So if you can handle this notebook, you can handle the whole full book. And of course, all of this example was only there's a lot of more topics to discuss, like the hypothesis testing. There's some more aspects about type 1 and type 2 errors, power. So this will be in the book, but I chose not to cover it in this notebook. What are the statistical assumptions? So when you use analytical approximations, you're building models where you're saying, oh, and let's assume this is normal. There's a lot of approximations and a lot of assumptions. So it will make those clear. So you're not just plugging into numbers into formula. more analytical approximation. So we talked about this whole example was comparing the difference between two means and two independent groups. There's a bunch of other scenarios. What if it's repeated measure? What if it's one group comparing to a theory? There's more formulas to learn. Building experiments. So this whole idea of random assignment, random sampling, very important. Perhaps the most important part. We'll touch on that. How not to make mistakes. Bayesian will be one section. We'll talk about Bayesian statistics, which is out of scope, but important because, again, many more advanced topics in statistics are Bayesian. So I want to teach you the things that are in the textbook, you need to know for school, but I also want to prepare you for more advanced stuff. So we'll do an intro to Bayesian. And what is the best way to learn is to do practice problems and exercises. So there will be a lot of those notebooks like this where you can run things on your own and where you have to fill in the details. Okay, so this was statistics. This was inferential statistics. Chapter 3 of the book, which is the main chunk. There is another topic though called linear models. Essentially, up until now, we were just comparing two groups, like 100 hours of statistics or 0 hours of statistics. What if we want something continuous in between them, like 0 hours, 10 hours, 20, or like an effect size, not just like all in or 0, but a smooth. So that's called a continuous predictor. In other words, what we're doing, the experiment is not just on or off, but like a smooth control knob. So we'll do another experiment in the 4th notebook where we study that. It will be much shorter, but yeah, it's really important because it's one of the other power tools in statistics. So there's a whole chapter 4 on linear models. Okay, to be continued in the next video.